If you looked at the last lecture, there was something you might have caught in my discussion about the angles in the final formulation of the heterotic string. This something has to do with what exactly is a dimension. In string theory, it is often said that strings require extra dimensions. That, in fact, is not quite true. And in this lecture, we're going to talk about that. Now, in science, of course, ideas come into fashion and, with the use of experiments, go out of fashion. Prior to Einstein, the scientific establishment believed that light was similar to all other known waves. And in particular, all other known waves must have a medium in which they propagate. Water waves, after all, travel on water. Sound waves propagate through the air. Since there's no air in outer space, there's no sound. So, since Maxwell's equations described light as a wave, even Maxwell thought there had to be something that supported these waves. This something was called the luminiferous ether, or ether for short. Now, the previous lectures have also covered the discovery of Einstein in the form of special relativity. And in special relativity, Einstein tells us that the way that one measures time and space actually depends on the kind of motion one is performing. But an important consequence of Einstein's idea is that although things appear to be different to different observers, that doesn't mean something is actually happening to an object. Now, what do we mean by that? Well, in order to illustrate, let's use my arm. If I lay my arm directly out in this direction, you could come along with a yardstick and measure its length. Let's say you got 3 feet. If you laid the yardstick in this direction, you would get 0 because my arm's not pointed in that direction. So you could write two numbers, 3 and a 0. On the other hand, if I bring my arm to this position, the numbers that you write are very different. You would write 0 for that direction because now the yardstick doesn't measure anything in that direction, but you would measure 3 feet along this direction. Now, nothing actually happened to my arm as I swung it back and forth. It's the same arm. It's just that the two mathematical descriptions are different. The important thing that Einstein realized is that this is what happens to time and space, that the time that you measure, if you're one frame of reference, and the lengths that you measure in that frame of reference can differ from the measures made by someone else in a different frame. But that doesn't mean that something actually happens to the object. That's the important message. In fact, the mathematical description of how you trade the time as measured by one observer and the space as measured by one observer and compare those to the time and space measurements of another observer are given mathematically by a formula called the Lorentz transformation. You notice they're not called the Einstein transformations. And the reason is because they were actually written down by another physicist by the name of Lorentz. You see, Lorentz also believed in the ether. However, when people did experiments to try to measure the velocity of the Earth relative to the ether, they got no results. They got null results. There was no obvious way to measure the ether. One way to explain this result is to say that the devices with which you're making the measurements were actually shrinking, and therefore that's why you didn't find the measurement that you were looking for. So that's a distinction between Einstein's view that there's nothing going on with the object. It's the relationship between the numbers that are changing and the previous point of view about the ether. Now, so the ether has gone out of fashion in physics. On the other hand, the idea of quarks, as we've talked about in this presentation, is very much in fashion in physics. We have lots and lots of experimental evidence that quarks exist, even though no one has ever isolated a single quark in a laboratory. So some ideas we believe in, others that we don't. How do we distinguish? Well, as I tell freshmen in my physics classes, physics is not what we write on the blackboard, it's what is happening in the laboratory. So if you find the evidence of the quarks, we are forced to believe them. Now, in string theory, we have this idea of extra dimensions, but we have no experiments yet that force us to believe that they have to be there, even though you will often hear in many discussions of string theory that string theory requires extra dimensions. This statement is technically false. String theories are consistent with extra dimensions. They don't actually require them. And this confusion actually turns out to be tied up with something that we talked about in the last lecture. We used the word dimension. And so the question is, what exactly is a dimension? Well, from the point of view of adding extra dimensions, which we sometimes call space invaders, that's the extra dimensions that you hear about often in string theory, they're extra pieces of space that come into existence. Now, this idea that these things are there is, in fact, part of the standard view of physics as is widely accepted now. In fact, during 1999, two physicists by the name of Randall and Sundram proposed a view that perhaps our universe is described in a larger world as if it's a plane of glass. This is called a brane, by the way. And these kinds of views of physics are called brane world scenarios. If you believe in brane world scenarios, it turns out that certain things in physics become much more obvious. For example, we've talked about the coupling constants in nature. Here we, in fact, have a plot of them. In our world, the gravitational force is the weakest of the force that act on matter. Then there is the electromagnetic force, the weak nuclear force, and the strong force. So as we go up in this plot, we're looking at stronger and stronger forces. Now, why is gravity so weak is a question people have asked. Well, one way to understand that is if our world really is like a plane of glass, then perhaps some of gravity is leaking into the other dimensions. And that's what the brane world scenarios propose. So it certainly has something to commend it. And there are other reasons for believing in extra dimensions. However, we still have to come back to the question of whether they are real. Let's talk about extra dimensions and how it actually entered physics, because the idea of extra dimensions did not start with string theory. In fact, we can go back to the 1930s when a physicist by the name of Kaluza wrote a paper in which he proposed that we needed at least one extra dimension. This paper had difficulty being published. In those days, you had to send your papers to a great physicist. He would approve it, and then it would get published. In the case of this paper, it went to Albert Einstein. On Albert Einstein's first reading of the paper, he thought it was nonsense. But upon reflection, he realized that there was something very interesting about this paper. That is, if you allowed one extra dimension, then you could find Maxwell's equations among the mathematical results that lie in the extra dimension. Now, but the problem is, of course, no one had ever seen an extra dimension. This was fixed by another physicist named Oscar Klein, who pointed out that if this extra dimension were really very, very small, it would be very easy to overlook it. So often when people hear the words extra dimensions, they think science fiction. But let me give you another way to think of it. Suppose you were in a house that had many rooms, but that you had a door to one special room that was so small that you couldn't get into it. Then effectively, that other room is not there. If you were able to get into it, it would be pretty much like the rest of the house, but it's the door that's the problem. So one of the ways to avoid extra dimensions is to think about them as being very small so that we can't get into it, we can't shoot atoms into it, we can't shoot light into it. And if that's the case, then maybe they're there, but we can't detect them by ordinary means until we find the experiments that are precise enough to exceed the limits imposed by these small dimensions. So the Kaluza-Klein idea was actually started in the 30s, but then it went out of fashion until the 1970s. In 1978, a group of physicists were studying something called supergravity. We'll come back and talk about that in a later lecture. But they realized that the equations for the most complicated version of this theory were much simpler if they could introduce 11 dimensions. Wow, we're hearing the word 11 now. Remember, string theory likes 10 dimensions, that is 9 space and 1 time. This construction wanted 10 spatial dimensions and 1 time, so it goes up by 1. So when string theory actually had its breakthrough in the 80s, physicists were already talking about extra dimensions because of this previous theory called supergravity. Now, are the extra dimensions real? Well, it's easy to miss things in our world because we are limited by technology. When we looked at our denizens, we found out that the electron had a friend called the neutrino. The neutrino for a long time was thought to only come in one spin. It could only spin in a right-handed sense. because that's all we ever were able to measure. A few years ago, in an experiment called Super Kamiokande, it was verified that neutrinos that spin in the other sense actually do exist, but we simply had not had the technology to find them. So here you can go from an idea of something that's not there and you find suddenly it's there if you increase your technology. Now, this idea about extra dimensions has also shown up in another way. You'll notice that electric charge comes in chunks. Now, in the old days, we used to think that the smallest electrical charge was the size of that which the electron carried. The electron has negative that number, the proton has positive that number. With the realization of the existence of quarks, the scientific evidence showed us that electrical charge could come in fraction of 1/3 of that size. So a charge quark has 2/3 of the unit of the a charge quark has 2/3 the charge on an electron, or minus 1/3 the charge. So charge still comes in chunks. It's a smaller size. Why is that? Well, this is a question that actually physicists have worried about for a very long time. And one of the ways to answer that question was proposed by an English physicist by the name of Nicholas Kimmer. In 1938, he made the following observation. We've talked in this series of lectures about the fact that electrons only seem to come in two varieties, either spin up or left-handed variety spin down. That's kind of like electrical charge. After all, at that time, people thought electrical charge was either plus the charge on the proton, minus the charge on the proton, or zero. So there were three possibilities instead of two, but still they're discrete. So what Kimmer observed is something very interesting. He said, let's look at the mathematics of spin and try to apply that to charge. When you do that, you find out it can actually work. Now, he did this in the context of an actual system in which he was thinking on exploring, namely protons and neutrons. If you look at protons and neutrons, one's charged, the other's neutral. The neutron actually weighs a little bit heavier than a proton, but that's like 1 part in 1800. So they're almost the same in terms of their mass. So what Kimmer said was the following. He said, suppose it were the case that in some deeper level reality, protons and neutrons have the same mass. If that's the case, it's only the charge that distinguishes them. And then he had a brilliant proposal. He said, suppose that charge is like spin, and so that in fact protons and neutrons are not different objects, but the same objects spinning in different ways. And here we put the word spin in quote. It turns out that the mathematics works exactly fine, and this was borne out by the idea of isotopic charge space. Now, it's an imaginary space. It's not a space in which we can move, but it means that the mathematics of spinning objects that we're used to in our world can actually be applied to things that have electrical charge. So Kimmer's notion of charge says that there are things that are like angles, that mathematically behave as angles, but they're not dimensions that we have access to. Now, this idea that you can have mathematical quantities that are important for physics that have the properties of dimensions but yet are not is all over the Standard Model. We talked about this earlier. It's in fact this business that if two photons have a change that produce the same electrical field, then they're related to each other by something, some mathematical object, and this mathematical object, it turns out, acts like a dimension. So even if you don't believe in extra dimensions, which there are many physicists who don't, it turns out that when they write their mathematics for describing the electromagnetic force, that mathematics behaves in many ways as if the world in which we live has the usual 3 space and 1 time dimensions, and then one other dimension which is described by an angle. But this angle, of course, is actually the business about two photons producing the same electrical field. So the notion of dimension is not as simple as you might imagine from your everyday experience or previous exposures to the discussion of string theory. And in fact, it even gets more confusing because we have touched on the aspect of the heterotic string. So now let me tell you one of the dirty little secrets of the heterotic string. We've seen this diagram before. I've used this, I call this the lariat diagram. And we've used it in many, many ways in order to describe polarization of light and in order to describe what's going on with standing waves, left-moving waves, and right-moving waves in this heterotic string. I'm going to use this in one more way and tell you a secret. You see, the standing wave mode, which we have used in the middle, corresponds to one of the strands on the string that describes space. So you need 9 of these standing wave modes to describe the space of the heterotic string, and then you need one more to describe the time. And now it's a standing wave mode, so we can watch it vibrate back and forth. But now we can do something different. If I took the 2 pictures on the side, and this kind of looks like Mickey Mouse. So let's imagine we blew up the 2 circles on the side and superimposed them on the middle. Then all that would be left is in fact the middle picture, and you would see a standing wave vibrating both up and down and nothing else. Can we reverse that process? Can we take a pure standing wave mode and pull it apart into its left and right movers? Here's another way to look at a standing wave that we've used, namely take a standing wave of the heterotic string. And remember, when I show you these pictures, I'm actually thinking about equations. So here's a standing wave mode. There is a process known as Fourier analysis, which is very well known in mathematics. It goes back to the 18th century, to the French mathematician Fourier. And if you apply this mathematical tool to the standing wave, what you can find is that it is exactly equal to a mathematical expression for a left mover and added to the mathematical expression for a right mover. So left and right moving waves, when added together, gives one standing waves. Now remember, in the heterotic string, when we say standing wave, we also mean something that's neither left mover or right mover. Well, those were the dimensions. And so therefore, it means that in string theory, if you think you're looking at a dimension, you have to be very careful. Because anything that you think is associated with a standing wave actually can be pulled apart mathematically into left movers and right movers. And why is that important? Well, it turns out that the angular variables, the things that are associated with the change in the photon, are always either left movers or right movers, but they're never standing waves. If you have this understanding of string theory, then it has a kind of flexibility about it. Namely, what you think is a dimension can be pulled apart and traded. So you go from a theory with, say, 10 dimensions to a theory that has less, but in the process you have to introduce more charges. Because effectively what you do is you trade off directions for charge. Now, this idea is actually a very potent one because it means that in studying the mathematics of the heterotic string, there are 2 alternatives, and it's not just the heterotic string. All string theory has this aspect, all closed strings. There are 2 alternatives to interpret the mathematics that one is looking at. The one that is popular is to look at the mathematics and say, we are seeing the presence of extra dimensions. By Mr. Fourier's mathematical trick, an alternative version is available where you can say, no, part of what you think are extra dimensions are actually these angular type of variables that are associated with the change of force-carrying particles. And so the notion of dimension in string theory itself morphs into become something that is much more flexible. So string theory has this really strange aspect of it that what you think is a dimension may actually be 2 kinds of charges, left charge and right charge. Now in the heterotic string, we learned that all right charges go into this number 496, and we were in 9 spatial and 1 temporal dimensions. Now let's imagine an experiment. Let's take one of those 9 mathematical objects that we think of as describing the space of the heterotic string, and let's pull it apart as I've described. what do you get then? In fact, let's not stop with just pulling apart one of them. Let's pull apart precisely 6 of them. We go from an object that exists in 10 dimensions to an object that exists in 4. Well, gee, that looks a whole lot like our world. Because in our world, we have 3 directions: front, back, left, right, up and down, and time. So the mathematics of the heterotic string turns out to allow one to go down to 4 dimensions, but in the process, you have to introduce more than 496 charges. And now you might also be worried about the corresponding left movers, because remember I said every time you take a dimension, you pull it apart to get a right piece, which is a charge, but there's a left piece that's left over. So what's this left piece all about? Well, shortly after the period that I was working on string theory, and we found in collaboration with my friend Warren Siegel this 3rd score for the heterotic string, we actually pursued this idea of pulling the string apart. And when you do that, what you find is another formulation of the heterotic string. It has more charge than the original version, and it has something else the original version does not have. When we went through the denizens, I pointed out that nature is very prolific in an interesting way. We have the electron. We have a copy of the electron that's 200 times as heavy. It's called the muon. And then we have a 3rd copy of the electron, which is 1,700 times as heavy. It's called the tau particle. When one writes a string theory in 4 dimensions, what you find is that the particles in the theory come in copies. And so in fact, a string theory in 4 dimensions looks more like our world than a string theory written in higher dimensions. So in some sense, you trade space for charge and copying. But this is a very natural explanation for why copies exist. Why is it that the electron has a copy? Well, without string theory, we have no way to answer this question. With string theory, what we can see that it corresponds to is that in some sense, it's an extra, what we used to think of, direction that has been pulled apart into a charge piece and a piece that is responsible for what we call family number in the standard model. So string theories are more complicated than you thought. They're more complicated than most physicists thought, actually. So this idea that you can pull them apart, we've described in terms of words, but let me give you a different picture. In fact, most of the people who work on string theory and most of the discussions that you may have heard tell you about this process called compactification. Now, how do I understand compactification? Well, suppose other directions really are out there in some sense. And if they're there, let's imagine, we've already imagined that they're small, but let's imagine that they're incredibly warped. In fact, in most discussions of string theory, you'll find discussions of these warped extra pieces that are called Calabi-Yau manifolds, at least in their most popular guys. It turns out that physicists are prolific in the ways that they can warp things too. So there are other ways of warping besides the Calabi-Yau manifold. Now, what's the difference between taking an extra dimension and warping it and starting with these extra angles? Well, the difference is that you actually have to do something to warp an extra dimension. And if string theory really allows extra dimensions, then they ought to explain why you have to warp them. That's something that we have never seen a consistent and complete explanation given in the context of string theory. On the other hand, if we start from the point of view that string theories ought to describe our world as we see it, then by definition almost, we should allow for the string theory to give us the copying processes that we see in the standard model, as well as allow the string theory to directly let us see the angular variables that are not associated with actual motion, but associated with the changes in objects like the photon. If you take this view, then string theory comes to live comfortably in 4 dimensions. And in the 4-dimensional point of view, it's not a question about warping because the theory has no options. Whereas if you believe in extra dimensions, the hidden question is, why did the theory warp itself? This is a question that we don't have an answer for. Now, The actual settling of these questions is going to probably take decades, maybe centuries. Is string theory an actual four-dimensional construct, or is it a higher dimensional construct where you have compactification? Well, the point of view of four dimensions I should also make some comments about additionally. This is not just my work. In fact, in the middle to late 80s, there were three groups of physicists who seriously studied this question of four-dimensional strings. There was one group led by a physicist whose last name is Antoniadis. He was joined by Backus, Kunis, and Wendy, and they extensively studied the idea that the heterotic string is an actual four-dimensional construct, and they use a particular mathematical approach that are called free fermions. That's a way of saying that we'll work with, remember that we talked about the two descriptions of heterotic string, that it had a bosonic description and a fermionic description. Well, they essentially used all the fermionic description. A separate group of physicists that was composed of Dieter Lust, Stefan Tyson, and G. Zupanis used a technique called the covariant lattice. In the covariant lattice, that's like using the old bosonic formulation totally for the heterotic string that we discussed in the last lecture. So at least three groups of physicists have concluded that string theory really is can be interpreted as a four-dimensional construct. The drawback in this is that all of these objects as four-dimensional theories are much more complicated to write than their higher dimensional analogs. Now, let me return to the discussion of warping, because I told you that there was more than Calabi-Yau. Well, in most recent years, physicists have been looking at things called G2 compactifications, spin bundle compactifications, and they've added an additional concept called fluxes. So these are all different mathematical tools for imagining starting with higher dimensions, rending and bending the space in some way, and getting something that winds up with a four-dimensional description. But there's an interesting question about this. You see, we live in a particular universe. So if you start with a string theory in some higher universe and you want it to come down to four dimensions, if you believe in higher dimensions, you've got to explain the warping. In particular, you have to pick the warping that agrees with our universe. Well, every few years, a physicist comes along, or a group comes along with a new way of compactifying. So we have no guarantees yet that if you believe in the higher dimensional point of view, that we have figured out the right way to bend the extra dimensions to produce our world. On the other hand, if you start with the four-dimensional view of string theory, start with the theory where the parts of our world, that is the standard model, which its carriers, are present in the string, and we know how to do that. And then it turns out that the string requires you to add many more parts that we don't see in the standard model. That's something we don't quite understand the process for doing. That's in fact one of the unsolved problems for string theory. It involves something called modular invariance, a very complicated process. If one day, however, we discover how to do that, we'll be able to write many copies of the string that contain our world and other stuff. Gee, that other stuff might worry you. Well, in lecture 1, we talked about stuff called dark matter, things that are not like the electron and the proton. Well, in a four-dimensional strings, you copiously produce dark matter. So in fact, as far as string theory is concerned, it's a good thing that dark matter is out there, because that's the price that we pay for bringing a string down to four dimensions. So, are the extra dimensions quark-like or string-like? We don't know. I want to end this presentation by showing you the difference between the mathematical description of the higher dimensional strings and the four-dimensional ones. You'll see for yourself why so many physicists have chosen to believe that we live in a universe of higher dimensions, but to which you have to bend the extra directions by this process called compactification. Now, I've shown you part of these scores before. Remember, for the heterotic string, as first found by the Princeton String Quartet, their papers contain essentially two scores. So I've shown you these two scores. Let me quickly put them up again. That's their first score. That's their second score. And then there's this third score that I personally was involved in with my colleague Warren Siegel. Now, all of those mathematical expressions I've shown you describe theories in 10 dimensions. This last one is everything that you saw in the last transparency plus this extra stuff. It's more complicated. It's more difficult to write. So, in many people's minds, the ones that are simplest to write are more elegant. But, you know, nature does not necessarily follow our rule for elegance. In fact, Einstein once said, in the search for truth, leave elegance to the tailor.